We have an insulated counterflow heat exchanger, just like the one we've shown. It operates at steady state with water entering as saturated vapor at 1 bar and a mass flow rate of 5 kilograms per second and exiting as saturated liquid. So let's do this. Here is my water on this side. It comes in as saturated vapor and goes out as saturated liquid. It's always 1 bar, right? And we have the mass flow rate is 5 kilograms per second. Let me ask you, what's happening? It's going from saturated vapor to saturated liquid. What's happening to the water? It's being condensed. Do you have to transfer heat out to condense it? So it's coming out of this fluid and going into that fluid. So guess what is our hot fluid? Our water is our hot fluid. Sometimes you have to work to figure out what's happening here. Which is my hot fluid? True? Now, it's 1 bar. Can you tell me what is the temperature of it coming in? Steam, 1 bar, saturated vapor coming in. What temperature is it? 100 degrees C. Now, what is the temperature of it going out? It's 1 bar, still 1 bar, but it's now saturated liquid going out. What is its temperature? How can you have heat transfer out of water if the temperature didn't change? Phase change, it's condensing, and we call that not the sensible, because at first it doesn't make sense. We call it the latent, as if it's hidden. Latent heat. Hidden, latent. All right. Little jargon there. Let's take a look at the other side. It's air on the other side, true. And the air comes in at 300 Kelvin and 1 bar and exits at 340 Kelvin. Does the temperature change make sense for the air? It went up. That's true. There was heat added to it from the water, from the steam that's condensing. There's negligible pressure drop, so 1 bar, 1 bar, 1 bar, 1 bar. The effects of motion and gravity are neglected. T naught's 25, P naught's 1 bar. Determine the mass flow rate of the air. Nothing to do with this class, all prerequisite material. Change in the flow exergy rate of the water. That one, yes. But let's go step by step. So for part A, how do I calculate the mass flow rate of the air? This is the mass flow rate of the water right here. Do a control volume analysis. Do a conservation of energy for that control volume. True? And so you'll be left with 0 is equal to mass flow rate of the water. You're coming in with its enthalpy at state, I didn't label these states, did I? 1, 2, 3, 4. Is that consistent with our previous notation, 1, 2, 3, 4? Then it's nice to be consistent with the notation used in the book. So it's H1 minus H2 plus m dot air, H3 minus H4. We rearrange. We find that m dot air is equal to m dot water times H1 minus H2 divided by H4 minus H3. True? And then H1 minus H2. Is that just HFG? It's just HFG. Comes in saturated vapor, goes out saturated liquid. Okay. Now I don't have a big temperature change for this air. Could I put C sub P of the air and then T4 minus T3? Would that work? Sure. Or you could look up the H at 340 and the H at 300 out of the table. Either one, you'll do that, and you calculate now the mass flow rate of the air is equal to 280.6 kilograms per second. That's the answer for part A. Change in the flow exergy rate of the water. What is that? We're asked to calculate m dot water times EF1 minus EF2. Isn't that what we're asked to calculate? So how do I calculate this property? Well, the mass flow rate of the water is given. It's just H1 minus H2 minus T naught S1 minus S2. True? That we already said was HFG. This is just S of G minus S of F, or SFG. And we calculate the answer for part B. And there's really, I mean, just leave it as on the left-hand side of the equation, EF1 minus EF2. They don't introduce a compact little symbol for that, but it's what is the exergy provided from the hot stream, and we calculate that's equal to negative 220, hold it, not negative, 2,265 kilowatts. So it's coming, it's a higher flow exergy. EF1 is greater than EF2. True? Okay. Now that's the answer for part B. What is the change in the flow exergy rate of the air? Well, it's the mass flow rate of the air times EF coming in at 3 minus EF 4. Okay. Or you could put EF4 minus EF3. If this we know is the in, that's the out. So this is what came out of the fluid, out of the water. The air, we know it's actually coming into the air. So if I want a positive quantity, put a 3 there. Whoops. Put a 4 there and a 3 there. See, that's a positive answer for part C now, because it's what's being picked up in the air. All right, just you have to calculate M dot A, and then you have to have H4 minus H3 minus T naught S4 minus S3. How do I calculate the change in S for air? It's right. It's S4 naught minus S3 naught minus R, natural log of P4 over P3, but they have the same pressure, so that term just goes, and so we just have out of the tables that one. Because the pressure didn't change, this term, it was 0 in the S4 minus S3 calculation, and these are just a function of temperature. So this is a function of 340 Kelvin, and this is a function of 300 Kelvin. You look those up in the air tables as well as the enthalpies at 340 and 300 Kelvin. And you can calculate then that rate of change of the flow exergy with the air. So M dot A EF4 minus EF3 becomes 763.5 kilowatts. That's the answer for part C. Now, you notice that what came out of the hot steam, 2,265, where did it go? Only 763 went somewhere useful into the air. So the destruction is the difference, isn't it? And so the destruction, the rate of exergy destruction is 1502 kilowatts from the exergy balance. It's the difference. Now, that's the answer for part D. And then what is the exergetic efficiency? Well, the exergetic efficiency, again, is what you require or what you want to happen. I want it to get into the cold fluid, 763.5 kilowatts, out of what cost? What was the driver? It's the 2265 kilowatts. So the exergetic efficiency for this heat exchanger is around 34%.